The project that we have created is a smart container that optimizes plant growth on spacecraft for long-term space missions by controlling the temperature and humidity. The smart container has two sections. It has a water tank on the right and a growing chamber on the left with a laser-cut partition in between. Inside the growing chamber there is a raised platform that contains the growing plants. There also are two temperature and humidity sensors and a 225 watt heating bed. The platform is raised so that when the heating bed turns on, the soil does not overheat and kill the plants. The water tank contains a 200 watt water heating element and a water level sensor. The control system that we have implemented has three control variables. The first control variable is the temperature inside the growing chamber. If the air inside the growing chamber is too hot, the control system will turn on three fans that are located at the top of the tank. If the air is too cold, a heating bed at the bottom of the tank will turn on. The second control variable is the humidity inside the growing chamber. If the humidity is too low, the control system will turn on the water heating element inside the water tank. This will warm the water inside the tank and cause vapors to form. The vapors will then travel through the vents in the partition wall and make the growing chamber more humid. However, if the humidity is too high, the fans in the heating bed will turn on and dry the air inside the growing chamber regardless of the temperature. The third control variable is a safety mechanism to prevent the water heating element from burning out. If it monitors that the water level in the tank has fallen below 20%, it will prevent the water heating element from turning on. The system is controlled via a code written in the Arduino IDE and was uploaded onto an Arduino Mega. The current temperature, humidity and water level are displayed on an OLED screen along with the status of the fans and heaters. The information is also displayed on an app that connects to the system via Bluetooth. The system can also be overridden via the app to change the desired temperature, humidity, and the fans and heaters can also be turned on or off. However, if a user is not connected to the container via Bluetooth, they can still override the system using an infrared remote control. We face a number of issues when creating the smart container. The first issue was that we did not have a power supply that provided a large enough current for the heaters to work. The power supply we then purchased meant having to hardwire it with a cable. This meant having to prepare a risk assessment and also having a qualified member of staff wire the power supply themselves. The second issue was that the original water tank design began to leak and therefore we had to redesign it. The new design was larger and therefore the raised platform also had to be changed as the current one was too big for the new design. The last major problem was being able to test the container 24/7. Since the container has water and electrics within close vicinity, it had to be constantly surveyed in case any problem should occur so that it may quickly be turned off. Due to this, we could only run tests between 9 to 5. However, this greatly affected the quality of the tests as plants could not grow in optimal conditions when this container is turned off. This time-lapse shows the experiment that we ran over 2 days, with grass growing both inside and outside the smart container. The grass on the right was cut from inside the smart container. It appears to have grown faster and with better quality. The success of this project illustrates the need for smart containers that optimize plant growth. The benefits of such a container in spacecraft will not only allow astronauts to have a fast-growing source of fresh vitamins, but will also help providing fresh water and oxygen during the long-term space travel.